Okay, welcome back. Today we're going to work an example problem from particle equilibrium in 2 dimensions. So we have a crate. That crate is supported by a cable that goes up here to this point, which we'll call point A. At point A, there's a ring or some other connection device that connects to 2 other cables. One of them goes over here to point B, which is basically a ring connected at a wall. The other goes over to point C, which is similarly a ring connected at a wall. You'll note that point C and point D are drawn horizontally to each other. So if we consider this to be, say, the y-axis, the y direction, they're at the same elevation y. Okay. Also, some information is provided to us that if you look at kind of this triangle right here, it's 4 feet here and 4 feet here. And it's 3 feet and 4 feet here, okay? They also tell us that this cable that goes from A to C can support a maximum force of 300 pounds. So it has to be equal to or less than 300 pounds. And that the maximum force for cable AB, the cable that goes from here to here, can be 250 pounds. So it has to be 250 pounds or less of force in that cable. And the question is, what's the maximum weight of the crate that's supported by the cable, the vertical cable? So how do we start these problems? The first step in starting these problems is to write a free body diagram. So we might call that step number 1. So the first part of step number 1, is to draw the body. So since we're in the chapter on particle equilibrium, we're literally just going to draw a dot. Well, the question is, where is that magical dot? When we deal with things that are connected by cables, etc., what we're looking for is where most of the forces intersect. So if I look right here, the force of this cable and that cable and that cable all intersect right there. So that's going to give me, you can think of it, lots of information to work with. So this is really point A. The second step is to draw the forces that are being applied. So there's a force in this cable, right? Cables are always under tension, so cables can only pull on things. There's a force here. So this cable can only pull on things. Right? There's a force down here to the cable that's connected to the crate. So here are cables. Now if you look, you should see that you have enough information to recognize that that's 45 degrees. And that this is a 3, 4, 5 triangle. So we've indicated the forces, we've indicated some information relevant to the direction they point. We also need to label them. So I'm going to label this force the weight of the crate, right? So if the crate's pulling down on the rope with its weight, the rope has to be pulling down on this ring with the same weight. Of course, ignoring the weight of the actual cable. We're going to call this one FC. And we're going to call this one FB. The last thing that we need to include is a coordinate system. So we're going to say that this is the X direction and this is the Y direction. So that's step number 1. See, there's lots of sub-steps. Step number 2 is just to write the equations of equilibrium. So if we've drawn our free body diagram correctly, we can go straight from our free body diagram over to the equations of equilibrium without having to refer back to this original drawing. Sum of the forces in the X direction equals 0. That is equal to minus 3/5 FC, where I've simply taken this force and I've taken the X component of it. Points in this direction and it's 3/5 its magnitude, plus the cosine of 45 times the force FB. So I've simply taken this, taken the X component, points in that direction, which is the positive X direction. We do the same thing in the Y direction. Sum of forces in the Y equals 0. So this is a positive 4/5 FC plus the sine of 45 times FB minus WC. So now we have equation 1 and equation 2. So now we need to see if we can solve these equations. If you'll notice, you have 3 unknowns, FB, FC, and WC, but only 2 equations. That means we need 1 more piece of information. If we look back here, we have this other kind of extra information that the problem gave us. It said, look, AB can't be any bigger than 250, and AC can't be any bigger than 300. So let's assume that one of these 2 is equivalent to its maximum, and see if the other one meets its criteria as well. So, if we were to say that AC, the force in that AC is actually equal to 300 pounds, that means that FC equals 300 pounds. So this is, well, if FC is 300 pounds, what does FB equal? If we can use equation 1, we can show that if FC is 300 pounds, then FB equals 254.55 pounds, which is actually too big. So that can't be true. Let's check the other way. If FB is equal to 250 pounds, which we're going to assume, then also from equation 1, we find that FC is equal to 294.628 pounds, which is less than 300 pounds. So we're okay. So FB actually equals 250, and FC equals 294.628. Once we have that information, we can use equation 2, or I should say we can solve equation 2 for WC. And if we do that, we'll see that WC equals 412 pounds.